it will start moving. See, it went there with the trapezoidal velocity profile here. So you can see Cartesian space trapezoidal planning. I've already told you about the topic and all. So basically, what is a Cartesian planning? So the space I am, what is the planning method I am using, and which type of Cartesian method I am using. Like I am using line, I am using start motion. So it's coming in joint space. Only joint 3 is moving. Now I will go to home again, the joint space. Now everyone, welcome back to my channel FusyBots. It's been a long I have uploaded any video on my channel, but let's start with a very interesting topic for today, that is Cartesian space planning for 6 degrees of freedom robots with trapezoidal velocity profile. Okay, so as a reference I am taking a UR5 robot for my experiments. So you can see I have defined a position. I am using Gazebo. I have already launched my code. You can see here I have launched my code. So this is the basic UI I have made for my robot. So let's get the status of the robot. Now this is the current Cartesian position of my robot, and these are the joint angles of it. Now suppose I want to move in Z direction. I want to go to 0.45 and here I want to go to 0.2. I am in Cartesian motion. So let's start the motion. Now you will see it will start moving. See, it went there with the trapezoidal velocity profile. So how a trapezoidal velocity profile works, it went to maximum, then be at the maximum velocity. Maximum velocity is 1 AR, it's low. And then it will decelerate from there. So this is the basic function. Now I will also be showing you my blog. So this is my blog. I have already uploaded this on my website FusyBots. So we'll be taking reference from here. So you can see Cartesian space trapezoidal planning. I've already told you about the topic and all. So basically, what is a Cartesian planning? So there are two types of planning. One is a joint space planning and another is Cartesian space planning. The major difference is while I'm doing a planning in Cartesian space, I'm making sure that my trapezoid, the velocity profile, is on my XYZ position and orientation RPY. When I'm doing in joint, I'm making a trapezoid in each of my joint velocities. So that is the basic difference between a joint space planning and a trapezoidal space planning. And the main difference, the core difference between these two is the joint space planner always try to use the shortest time, while Cartesian space planning always make the shortest path. So it will make a line between the two paths until and unless you are explicitly defining a path planner for this. Like suppose you want to go in an arc, you want to go in a spline, that is a different case. So that is a Cartesian space planning. So this is some graphs where I am going from one position to another. I have made this program in Python. So this is basically my interpolated path, and these are my slurp interpolation, that is quaternion interpolation. I will explain you what it is. Why use a trapezoidal velocity profile? So in joint space trapezoidal planning blog, I also shared you why we are using it. Basically, it is to maintain the smooth motion by controlling the acceleration and deceleration. We generally it's C1 continuous. Basically, we are accelerating, then staying there, and then decelerating. Okay. So in my joint space, I already explained that. Now, why do we handle? Okay. Now the thing is, why do we handle the position and orientation? Now, after this explanation, I will go to the code. In the code, you will see that the position part and the orientation part are taken separately. Why? The main thing is the end effector might reach the right position but may face the wrong way. Correct? The position may be correct, but the orientation might not. It might rotate too fast or too slow compared to its movement. Therefore, we have to take care of position as well as orientation both. Okay, so what we are doing basically here, we are fitting a trapezoid in two things. One is the position, that is the Euler distance between 2 points in a Euclidean space, and the distance between two quaternions in a SO3 space, spatial orthogonal group. So basically, we are fitting two type of trapezoids here, and we are taking the maximum one, the maximum time, which is taking the maximum time and fitting under the same time zone for both the trapezoids. Okay, how to do the calculations for that? First, we have the current state, we have the desired state. Compute the path length, current method, and the Euclidean distance. Now, compute the orientation length. That is, this calculation is happening in SE3 space, that is Euclidean space. The orientation length is calculating in a orthogonal space, SO3 space. Now we'll be fitting a trapezoid over these lengths. So I will take the maximum of path length, the orientation length and time, and I will fit a trapezoidal planar over it. Now comes the path parameter. What is the path parameter? It's very important for any type of path planner. So path parameter will traverse from 0 to 1, or you can traverse it from 0 to length of the path. And at any point, if I query any point, for suppose I'm going from 0 to 1, if I query any point between 0 to 1, it will give me the point, the correct Cartesian position at that particular path parameter. So I will parameterize my path with only one variable. So it will make the calculations easy for me. So at any point, path parameter is waypoint divided by maximum of the path length and the orientation length. We'll come to this again while we'll be exploring through the code. Okay. Then pass the path parameter to the Cartesian path. I told you it will go from 0 to 1. It's a simple linear interpolation, you can see. So in the Euclidean space, I am doing the simple linear interpolation, while in the orientation space I am doing slurp interpolation, that is spherical linear interpolation. So you know that these type of quaternions do not follow this normal algebra, Euclidean algebra. They follow a different kind of algebra in a spherical space. So for that we are using slurp. Now this is a basic code in which it's a Python code, just to show you how trapezoidal planar works. It's very basic, like you can go through it. Now there are some frequently asked questions. You can go to my website, that is fusybots.com, and go through this blog. You can go through this frequently asked questions. These are very important. Now we'll be coming to the code, the main thing. So this on the left side you can see it's my main executable file. On the right side you will see it's my path planner. How it's happening. Okay. So as soon as any command comes, first of all I'll take that command. So in that command, what all I will get? Basically, I will get what position I have to move, in which planning space I am, what is the planning method I am using, and which type of Cartesian method I am using. Like I am using line, I am using circle, what kind of Cartesian method it is. Okay. So this is my joint space planning. I already explained you in my previous video. You can go through it. Now I will come to my Cartesian space planning, how this works basically. So my Cartesian space planning I will take initial Cartesian position. Okay, so what is my initial Cartesian position? Then I will take my target position, where I have to go. Now I will plan from initial position to target position. Obviously that is very simple thing. So I will initialize my path planner. I will call a function of my path planner. As soon as I call function of the path planner, it will come here. And what it will take? It will take the initial pose, it will take the final pose. It will find the length between. So basically in init pose and final pose, I have my 3 position, 3 orientation, 3 position, 3 orientation. I will find the Euclidean distance in the position. I will find the orientation distance between 2 quaternions, and then I will pass it back. Okay, now this length will be used later on. So I have my Cartesian length. Now from the initial state I will take 0 0 to the final length. Like suppose in position I am moving by 2 meters, in orientation I am moving by 1.5 units. So I will initialize the trapezoidal trajectory planner in that. This trapezoidal trajectory planner will fit the trapezoid, and this trapezoid is same as we have done in the joint space planning. This is the same function I am calling, but I have used in the joint space planner. This is the same thing. Now as my execute function will start, it will go here, it will call it. I will find the path ratio. I told you we take the path ratio, and I will pass the path ratio to my path planner. And if I told you that my path parameter if I query any point to my function with this path parameter, for suppose 0.5, it will give back me that what is the Cartesian position at this 0.5 path parameter. How it works? I will give it the ratio. It will call this function here, linear path planner. Here it will take the ratio, it will take the initial Cartesian position, final Cartesian position, and it will calculate the interpolated position in between. And it will also apply the slurp in between 2, and it will give you the interpolated orientation between 2, and it will pass it back. Now I have my Cartesian position, but can I give it directly to my robot? No, I have to apply the inverse kinematics to it. So as soon as I get it, I will apply get joint angle. So get joint angles is my inverse kinematics function. As soon as I apply this function, I will get my joint angles. Now I will publish this joint angles to the variable, and that variable will be published back to my robot. So yeah, that's how it works. So now again I will show you my code. the main thing is the path parameter. The trapezoidal planar will be the same as in joint. The main thing is coming is the path parameter. You have to understand what is path parameter and how path parameter is used to calculate the Cartesian position. And from Cartesian position, we are just applying inverse kinematics and coming to the joint space. That is a very simple thing. So I will just switch on my code once again. Okay, so this is my robo. Now I will enable my robo. As soon as I enable my robo, okay, I'm starting my code again. So this is my robo. I will enable my robo. I will get the position here. Now first I will show you. I will move in the joint space. For suppose I am moving joint 3 to 0. Now I will start the joint motion. See, start motion. So it's coming in joint space. Only joint 3 is moving. Now I will go to home again, the joint space. Now I will go in Cartesian space. I will get status and I will go in Cartesian space. For suppose in Z I will go to 0.20. I will increase the speed in this case. Now I will go to 2.5. Let's see what happens. Nothing happened because joint space selected. Now Cartesian space, go. See, it's moving in Cartesian but in straight line. You can see how fast it's moving. Yes. So yeah, today's video, I think you got everything about how Cartesian planar works, how to integrate it with your code. The website, I recommend you to go to this blog. You will get everything. This is a basic Python code to understand you the concept, basically how all it works. There are frequently asked questions. Go through them. If you have any doubt, just comment on the video. Thank you for coming to my channel. Please subscribe to my channel, like the video. If you have any comments, feel free to comment on my video. Thank you. Bye bye.